Okay, so good afternoon. I remembered about this lecture this time, so that's good. And this will be our last lecture of this term. It's unlikely, I'll tell you this now, it's unlikely that I'm going to finish all that I mean to finish, so I might have to record a bit extra. I'm going to be short by about 20 minutes or so, I think. So I'm going to record a bit extra and put that online as well. And then if we got time at the end, I might come back in revision. We can just go over the bit we missed. So we might miss a bit on D to A converters, but heaven knows, we might not. Oop, no, wrong one. Okay, so the end of the last lecture, we were talking about this, or introducing this idea of noise shaping in this digital modulator. And the important concept is that we've got a different path through this feedback system for noise, which in this case quantization noise, and the signal. And we've tried to exploit this by giving the noise and the signal a different transfer function around the modulator loop. So remember this loop here. So we're saying we've got this loop here, and there's a different path for noise coming in here around, and there's a different path for signal coming in, and we can try to exploit the difference. And we noticed that there was a difference in the path through the system, or the transfer function through the system for signal. U to Z was the signal coming in here, compared with the error signal or noise signal, which comes in due to the modulator and its quantization error. And so there's a different transfer function for each, and if we can be clever about our choice of H of Z, we can maybe exploit this. And that's what we're getting to. And we looked at this and we decided that we wanted to have a low pass filter here to allow signal through our system, because our signal is in the low frequency, and we would have a high pass filter ideally for the noise up here, so that we can separate the two out, so we can effectively filter out the quantization noise because of this system here. And we looked at this and we said we got a first order low pass response, and we had to take my word for it that 1 over Z to the minus 1, Z minus 1 being a delay function, the Z transform. That's a low pass response. And then if we put H of Z with this response into our transfer function for the forward loop, and just do some algebra on the Z's, we end up with it being the equivalent of Z to the minus 1. And the important point about Z to the minus 1 is it is just a sample delayed by one time step. So it's a sort of a flip-flop D-type latch, something like that. So that's quite nice. And then the noise function has something that's slightly more complicated, 1 minus Z to the minus 1, so it's 1 minus a delay. And that turns out to be the equivalent of a high pass type function in the Z transform, because again, take my word for it, at DC Z has a value of 1, and at high frequency Z towards infinity. So you can say that at Z equals 1, 1 over Z equals 1, so 1 minus 1 becomes 0. So at low frequencies the transfer function for the noise becomes 0, and obviously as Z tends towards infinity, 1 over Z tends towards 0, so we end up with the noise being transferred at high frequencies. It just becomes a question of where is this boundary between low frequency and high frequency. But we have managed to separate out the noise, the quantization noise, from the signal in terms of frequency spectrum. So just quickly, it is possible to describe H of Z, this block here, as a feedback function in its own right, so we can call it G of Z fed back on itself, and if you then do the sums on that, it also becomes quite a simple response. So G to the Z, which is the bit inside H to the Z if we feed back on itself, just becomes a delay function itself. So all this is delay functions fed back on themselves, and it becomes a simple thing to implement, in principle anyway. So the whole loop just becomes a feedback, a delay function, digital delay function, with that fed back onto itself and put through, and then the quantizer just looks at it and then feeds that back on itself as well. So the system becomes quite simple in that respect, but complicated in its concept. There are alternative ways of implementing this. One possible way is to implement H of Z as a sampled integrator. And remember that a low-pass filter is an integrator, so we could actually use a switched capacitance type system again here, where this is switching and sampling the voltage here, and this is integrating it. And therefore you can make the whole modulator in switched capacitance form relatively straightforwardly with a couple of capacitances and a comparator and an op-amp. So this is all relatively straightforward then to implement in, although the timing in the maths starts to become a bit more interesting, and obviously the quality of the switches comes into play as well. So we've got some slightly complicated switches in here, but this is just an example implementation. I'm not saying it's the only way of doing it, but it's just to remind you that this switch capacitance technique that we've looked at is very versatile and can be used in these switch data systems. Okay, so it's always worth putting an example to get your head around this a little bit. But if, for example, we put in, and this is quite, if you follow this through, you're going to have to spend 10 minutes or so following this through. I'm not going to spend 10 minutes on it now. But if you say that we're going to put a voltage into our modulator, and let's call it 0.2 of a volt. So that's fed in here. It's not changing, so we've got a constant voltage coming into here. And this is our modulator system. And we have to assume some starting conditions for this. So let's just assume that we say we've got 0.3 coming out of here from the previous sample, and this means that the error this quantization can either go -1 or 1 in this case. So it will go, if it's got -3 here, it will go -1 here. So then we just follow the whole thing around. So you've got 0.2 coming in. We've got the previous sample of y to the n-1, which is -1 in this case. We've got the previous sample of x to the n-1, which is 0.3 from here. We add those up and we get 0.9. We then go to the next timing cycle, and we still got 0.2 coming in, and then we've got the various, we've got yn, we can from the previous sample coming in here. We've got 0.9, which is the previous x there -1, and you can see how we just keep clocking that through, where with a delay at this point here, and then this value then is clocked through. You end up with the output y of n being a combination of 1s and -1s in a seemingly random fashion, and that's the output. And how we say, how does that relate to this input of 0.2, which effectively we're trying to get some kind of handle on? Well, it's the average of all these 1s and -1s, and this is why you need to clock it really, really fast, because you need lots of samples to get a good average of to a good resolution of the input. So if you averaged all these, you'll find it comes to about 0.2. And if you averaged a lot more of them, it will be even being much more accurately 0.2. And you can see then how we start to get the output from this modulator. So we're getting a stream of data coming out of here, whizzing out of here, which if we averaged it would give us the input value. And this is how it all works. So that's fundamentally all that's happening. We're turning this into a stream of 1s, of which the average is the value of the input stream, is the input value. And obviously that average will change if this value starts to go up and down. But this needs to clock really, really fast compared with the frequency of change of this input signal. Right. So an alternative way of looking at it, if you're not that familiar with Z transforms, the concept can be got from a linear approach, just using S transforms. So we've got the same kind of loop. We've got noise, our quantization noise being added in at the output of an integrator. It's fed back in itself. Our input signal is coming in here. It's having the part of the output subtracted. The error signal is fed to the integrator, which then goes to our comparator. And this system looks like this in the linear function. So again, exactly the same applies. We can say the error is equal to x minus y, which is the difference between the input and the output. And if you work the transfer function the same as before, we end up with y equals noise plus e over s, which equals noise plus x minus y over s, because e is defined as x minus y. And you can just follow that through, and you end up with exactly the same double transfer function, one for the noise coming in, one for the input signal coming in S transforms. And we can maybe recognize these as a low pass filter, a single pole low pass filter, and this as a high pass filter, single order. So again, the noise is modified by a high pass response, and the signal is modified by a low pass response. So this is the same but without the switching and without the Z transform. So if you're not happy with Z transforms, you can get the idea from this, and it's the concepts that are important at this level anyway. So to look in a bit more detail at the magnitude of the noise transfer function, so we can start to our definition of Z, think back to the last lecture, was e to the j omega t, which is similar to the S transform as well, and that boils down in frequency terms to e to the j2 pi f over ss. Okay, and then we can just start to make the substitutions for Z in our transfer function for these values here. So our noise transfer function was 1 minus Z in the Z transform, which we can just substitute for that, expand that out a little bit, and we end up with this is sort of Euler's function for sine. So we've simplified down to sine pi f over ss multiplied by some rotating phasor. So the magnitude of that is just going to be 2 times whatever this is. So the magnitude of the noise transfer function is this function, which is a sine function, and it depends on the input frequency in relation to the sampling frequency. So whatever the sine of f over fs is, that's going to be the magnitude response of the noise transfer function. Now, we thought this was a high pass function. It turns out this is a high pass function, because when f equals 0, sine of f equals 0, and when f happens to equal 0.5 fs, 2 sine pi, put the value of f equals fs into here, you get 2 sine pi over 2 equals 2. So the magnitude becomes 2 at high frequencies, but is 0 at low frequencies. And this illustrates this noise shaping function. The noise has been moved from the low frequency area to the high frequency area. So we've got more noise now in the high frequency area, because the absolute magnitude of this can be 2 rather than 1. But in the low frequency, we get nothing, which is the majesty of this. So all we've got to do is make sure that we're not interested in the high frequency part of the sampling regime. So we apply oversampling to this, so we're sampling like mad, but our message is held within a frequency band that is much less than the sampling frequency. Now if we're oversampling, then we're just taking too many samples, so our message, our signal of interest, is now constrained to be within a low frequency band, as defined by the oversampling ratio. Think back to that. And at small values, sine pi f over fs is approximately equal to pi f over ss, for small values of this. So as long as this is the frequency of interest is small compared with the sampling frequency, this approximation holds. Just makes the sums a bit easier. And then we can apply this value of the transfer function into the equation we developed last week for the error power. So that pi f over ss just drops into here, and we have to square it, and we end up then with this response here, having integrated it, or we do the integration rather of this, and we end up then with q squared. Remember, q is the quantization error magnitude, pi squared over 36, 1 over OSR to the 3. Okay, so our new maximum signal to noise ratio now becomes, if we put that into this signal to noise ratio equation, 6.1.765 and 30 log OSR, which means now that because of this noise shaping function that we've got, doubling the OSR this time gives us a signal to noise improvement of 9 dBs, or equivalent to 1.5 bits, whereas before we only got an improvement of about half a bit or so. So we've gained, for the same amount of oversampling and a little bit of noise shaping, we've gained a significant improvement in our signal to noise ratio. If you go further and do second order noise shaping, we've just done the first order noise shaping, you can do the calculations again, and you end up then with this response, which is 50 log OSR. So we've gone up a square in this ratio here, and that gives us 15 dBs per doubling of the oversampling rate, or a 2.5 bit improvement in resolution, just for a doubling. Okay, so this is all very interesting. What does it actually mean in practice? So if we go back to our example of the 1-bit converter, which if you could have such a thing, and maybe you're starting to see how this might apply now. We calculated that with no noise shaping we would need 54,000 gigahertz of sampling rate to get anywhere close to a 16-bit signal-to-noise ratio for quantization noise. If we then put first order noise shaping in place, which we know how to do now with our delays and our little loop and our first order modulator, we can now get this response out of it, which means that to get to a 16-bit resolution of signal to noise, or equivalent of 16-bit, we just need now to have an oversampling ratio of 1513, which has now dropped down from this one to here, or rather, so the sampling rate drops from 54,000 to whatever the message bandwidth times 2 times the oversampling rate is now 75.5 megahertz. Now 75.5 megahertz is getting into the realms of being entirely possible. Sampling at this frequency is not impossible. If you then go to second order noise shaping, which is obviously a little bit more complicated in terms of the modulator function, but then the oversampling rate only has to become 115, and for the same size of or frequency width of message, we now only have to sample at 5.8 megahertz, which is starting to get quite attractive. You can go higher. People will investigate third, fourth, fifth order. People have gone much higher than that, but it starts to become a bit tricky to guarantee stability of such systems, and quite often you don't really need to go that far. But just be aware that this opens up a whole new ballgame of complicated systems that you can look into for this simple idea of single bit quantization and oversampling. So you can start to see the attractions of this, certainly from digital systems design anyway, because it's just delay gates and high frequency clocks, which is all good. So in sort of graphical form then, the noise power, or the noise transfer function for a system, the first one we looked at with no noise shaping, remember we said it was equally distributed across the whole sampling range. This is the Nyquist frequency here. So it's equally distributed, and our message would be have to be held within this area here. We have to sample at fs over 2. So with the noise shaping, first order noise shaping, if you plot it out, remember it started at 0, and at fs over 2 it got to a peak of value of 2, so this is a value of 2 here. We can see that from 1 here, so 2, and is a sort of a high pass response. So you can see that if you can constrain your signal bandwidth to be between 0 and f0, which is, so this is the ratio between these two is the oversampling rate, you can see that the first order response, the noise level is very low at low frequencies and is rising a bit towards the top end of your message frequency, but it's a lot less than the noise floor that would have been the case for no noise shaping. And second order, you can see you get a big improvement there as well, because you get this double inflection. So it's quite flat for second order, rises up to a value of well, I guess it's 4 up here. But if we're only interested in this bit, the noise floor here is very, very low. The noise up here is quite high, but we can filter that out because there's none of our signal in that. And that's a visual representation of how this system sort of works. And you can see it's called noise shaping because this noise floor has been shaped to be some hill of a thing, and we push the noise from the low frequencies to the high frequencies. And if we can filter that out, which it looks like it's possible to do, then it all works nicely. Okay, so at this point we've still got a bit stream coming out of this modulator. So this is where we've got so far. So we've got a bit stream whizzing out of here. We're going to need to convert this into a data word, because ATD system or digital systems like to have words of data. And the overall architecture for this looks a bit like this. So we would then feed our pulse stream into a digital low pass filter, which would take all those bits, feed them back on themselves again, and would recreate the digital signal as is shown in this graph here. So here's our modulator output whizzing through. There's the noise shaping. We then apply that to a digital filter with a cutoff frequency here that gets rid of all that noise and just allows our message to be here. And you can see that the amplitude, digital amplitude of the output of the digital low pass filter, you can just see that the output signal is starting to come into play. So we've got a whole series of digital words being thrown out of this thing at a very high frequency, you'll note. But this is oversampled. This is far too much data than we actually need. So what we can do is we can then apply something called decimation. And decimation is an old, effectively a Roman word, which means in Roman times they used to punish their legions by, if there was any insubordination, they'd line everyone up and they'd kill every 10th man, just as a lesson to the rest of them that it was better to fight and die than to well, fight and lose or run away. So that's the origin of the word decimation. So we're going to do effectively the same kind of thing, except worse. What we're going to do is we're just going to take out a lot of these samples that we don't need, because we only need them at the Nyquist frequency to be able to rebuild our filter, rebuild our signal. So we chop out a load of these things and it slows the data rate right down for us, and then we'll use an analog filter at the output here to recreate this if we wanted to. But we've got all the information needed in here to recreate our complete signal because of the rules of Nyquist. So that's quite neat, the idea. Actually building this digital low pass filter is quite a hard job to do because it needs to have a very good response, but decimating it's quite easy. So we move the complexity into this part here, and that's not part of our course, you'll be pleased to know, so we don't worry too much about that. That's where you really need to understand Z transforms. And I'm sure some of you have done digital filtering courses, so you'll be familiar with what could go on in here. Right, so the last bit that we need to cover in this respect anyway is another technique called time to digital conversion. And it's not commonly used, but it's a technique worth knowing about, because it's quite easy to build one if you're programming things like full programmable gate arrays or programmable logic systems. So it's an interesting way of being able to get analog signals into some of these systems without necessarily creating a bespoke A to D converter. So the idea is that you chain up these carrier blocks within, because these are all part of the blocks of the FPGA logic blocks. There's usually a buffer system in these things. You have to make sure you've got this buffer system in your architecture for the FPGA that you've chosen. But if you've got that, you can link these things together, and then when you actually start the conversion here with a start pulse, that takes time to propagate through this buffer, and then it turns on, or it applies the start signal to this D-type latch, so it's going to latch that at some point when the clock's gone. This one, the signal carries on, it propagates through here, it takes a bit of delay to get to this point, and then appears here, bit of a delay, gets to here, and so on. And what then happens is at the stop point, which is when your input voltage has crossed a threshold of a comparator, it actually clocks this thing, and whatever's appearing at this point here is then presented to the output. So you end up, if this pulse hasn't managed to propagate all the way through, you'll get ones to a certain level and then you'll get zeros beyond that. So you end up with one of these thermometer codes coming out of this point, which you can then read in parallel. So it's quite a straightforward technique. You need lots of these logic gates, but if you're dealing with an FPGA, you will have lots of these logic gates. And the typical delay through one of these buffers is about 20 picoseconds or so. So you just need to then calculate how long a buffer you want, and that depends on your clock cycle as to how many of these buffers you can actually fit in, because this is the fixed time in the system. But it means that you can have a sampling rate that's effectively very high in hundreds of megahertz from just cascading a whole bunch of logic together. And so some people have implemented some of these things. I should have a reference on here, somebody hasn't got it. I'll dig the reference out. So this is taken from a relatively recent research paper which shows an implementation of that. So we've got an internal clock that's starting everything off, and that starts the timer running. And what then happens is it generates a rising voltage this is the only thing you've got to put in is a resistance, and it uses the sort of stray capacitance across here to give us an RC time constant. So you can see that Vref is starting to rise up in exponential fashion, and then when that crosses the threshold of the input signal, which we're assuming isn't moving very much, that then stops the clock. So we've used an entire logic system, and the only thing we've had to put on the output is a resistor. Everything else is internal to this logic system, and that allows us to generate an A to D converter. And here's the output voltage. What are the details on this? So assuming a clock speed of 200 megahertz and a delay of 20 picoseconds through the system, you can get 125 levels in our delay line, which is nearly 7 bits of resolution. And if you clock slower than that, you can put more logic gates, if you like, in the train, and you can get a higher resolution. So it's entirely programmable by yourself. It's quite neat. This is a double-sided system, that's why it's got two of these. So he's doubling the speed of that. So that's quite a neat idea, really. So that was a quick run through of A to D converters. There are lots of trade-offs. Area of silicon, if you're into that kind of design, the power consumption, resolution, speed of conversion, and ease of implementation. All of these individual types of technique are, they're almost degrees in their own right to get to the bottom of how to actually work them properly. But at least you're now aware of some of these ideas and how they can be stitched together to make some quite interesting and exciting digital systems and analog systems as well. So worth understanding that, because at least then you can get some idea of what type of A to D converter to use for what type of application. So here's a sort of graph I've taken from a Maxim datasheet that shows as the number of bits of resolution, for example, go up, the conversion, that says convention, it means conversion time. The conversion time starts to go up, and you can see that the integrating ADC, as you get more and more bits of resolution, you end up with a much significant rise in conversion time. So if you want high resolution and short time, then you don't want to go for an integrating ADC. And these other ones tend to be fairly linear, whereas the conversion time for the flash converter is pretty constant, irrespective of the number of bits of resolution. But we know that the number of bits of resolution here means that we get, the higher we go in that, the more complexity we actually get in the circuitry and the number of components we actually need. In terms of component matching, as the number of bits of resolution goes up, we get much more requirements to have well matched components for these type of converters, whereas sigma delta types don't necessarily need good component matching. But there's a trade-off there as well. Number of bits of resolution and the complexity compared with the die size. The flash, we know, is the worst. It gives us a really huge area and probably a high power consumption as well. Whereas the integrating ADC, its complexity doesn't change with the number of bits of resolution. So that's just a sort of an interesting look at the trade-offs between these things. Yeah, you can just take the type that because you can buy all these in individual packages. You can buy a chip that's got an integrating ADC, or the parts for it in there anyway. You can buy certainly sigma delta ADCs in single packages. So it's just be aware of how they're doing it and what the compromises are when you actually come to choose one. Like all these things, for general purpose, you can probably get away with any of these, but once you start to get to the extremes or high performance, you need to understand which one is the best for the job in hand. Okay, so that's the end of A to D converters. We've got a little bit to do on D to A converters, which we can start here. We probably won't finish it today, but if we don't, I will record, as I said, a finishing little lecture. It'll only be half an hour or so, which will allow you to pick that up, and we might have some time in revision week to go over such things as well, depending on how Kaylee and Rumen get on with their timings. We haven't actually made any decisions yet about what's happening after Easter. We're waiting to see what the university decides. So it's still possible to make comments to me if you want to about this. What's likely to happen is that we will probably end up doing them as live lectures, and they'll be live streamed as well. But people are a lot better this year at live streaming live lectures and making it accessible for remote access as well. When we just have to see what happens. So it hasn't actually been decided yet. It may well be that a university decision happens that means that we have to stay remote anyway. Okay, so we'll let you know what happens with that going forward. Okay, so digital to analog conversion. So the last bit you'll be doing with me anyway. I think there's a midterm survey open now as well, so you'll only be able to comment on my part of the course there. I would urge you to fill that in and give us some feedback. Try to be polite. We do listen to it and we are trying our best. Be constructive in your criticism, don't be rude. But we're quite happy to have criticism, and if it's working well, as when you like it, then tell us that as well, because it's always nice to hear that we're doing a good job. This year it's been particularly difficult because I'm just talking to a screen at the moment. So yeah, if you've got anything to say, make use of the surveys and then let us know what you think. Right, digital to analog conversion. So we've got to do the opposite of the digitization process. So we're going to take a discrete time signal. We're going to try and turn it back into a continuous time signal. Ideally, we'd like to do this with perfect accuracy, but given that the digital representation is already an approximation of the real signal, we're going to be starting from a disadvantage straight away. So we can sort of see what's going on here. Most direct way is to take our signal, hold that until the next sample period, move to the next sample period and display that, so we end up with a chopped version at the output of our system of what we would ideally be the original signal we're interested in. And again, you can see that as we decrease the sample period, i.e. we get a lot more samples in this system, we'll be able to follow this a lot more faithfully. But even if we've just got this choppy function here, what we can actually do to that is we can low pass filter that with an analog filter, which we now know all about, and that will track the average of this response and will give us a good representation of the output that we want. And the question just becomes, how accurate is that going to be? Right, good. So the sample and hold has to be reviewed again, because unfortunately it turns out that the act of sample and holding actually has a frequency response of its own. And so the amplitude of any output signal from the sample and hold vector depends on the frequency of the input signal, which is a bit of a drawback in some ways. Well, in all ways, really. So we can explain this with a little bit of maths, sadly. We have an amplitude sample that is valid at only one specific point. Here it is, so that's what's valid. We don't really know what happens between this point and the next because it's discontinuous. We suspect it's continuous between it, but exactly what happens in between these 2 points we're just guessing. And we can describe that mathematically as this kind of function here. So we've got the height of the signal multiplied by the impulse at a time defined by however many time steps there are at that point when we're sampling it. So the practical zero hold sample and hold function takes these impulses and converts them to held samples. So instead of sampling at a spike, we actually hold it until the next sample level, and we can define that mathematically with this thing called a rect function, which looks like this, centered around 0 in this case. So we need to modify that slightly so that it starts at 0. But you can see the general idea of what we're trying to achieve. We're trying to take our impulse response and hold its peak until the point of the next sample response, and that then becomes defined by this transfer function here, which is really just describing mathematically this type of thing here. And you just have to remember the definition of rect is given by these discrete points in time which describe the square wave, I suppose, pulse, whatever. So, well, that's sort of obvious, I suppose it is. So we just reconstructed it because we can now say that our output signal is going to be made of a whole bunch of these sample and hold features as we go off in time. But now we can do a Fourier transform with this impulse response because this is in the time domain, and this gives us sin x over x response, which is interesting in its own right. So we've got something in terms of frequency which is quite wobbly, where sync is defined as a sin x over x response, and that has that kind of frequency response. So we can see that we're starting to get something that's now getting a little bit messy. And then we multiply that by the frequency spectrum of the sampled time signal, and this ends up giving us so the frequency of the sampled time spectrum is given by this, and we end up then with the overall response of our function looking like this. And the interesting thing to notice here is that this response here, we now got a sin x over x response here, modifying the frequency response of the whole signal. And it's best viewed, have I got a graph of that? Yes. So that's best viewed in this type of response. So this is in the sort of time domain. We've got our time, signal following the response quite nicely. But in the frequency domain, this is the frequency response of our message, if you like, bandwidth of our potential signal. But we've got this sin x over x envelope that's caused by this sample and hold function over the top of it, and you can see that the multiplication of these two frequency responses means that anything here is going to be reduced in amplitude because of this sync x response, which drops down at this point here at sampling frequency. So even at the Nyquist frequency, which is halfway between these two, we've got a significant fall in the amplitude response of the sample and hold system itself. So we're starting to modify the frequency response of our signal by the very fact of sample and holding. And maybe this shows it a little bit better. Talking about this, which is that people have called the first Nyquist zone. So that's the sampling frequency. This is half the sampling frequency. This is where we can put our message and not have it aliased. And you can see that the overall response to that is falling away. And we can work out exactly how much because we know this is a sin x over x response. And if we do that, in principle, at the Nyquist frequency of fs over 2, which is here, the frequency response of the system will be sin x over x, where we've got sf over 2 over sfs, which is the 0 point, over this thing in the bracket but without the sign. And if you work that through, you end up with 2 over pi 0.636 or minus 3.92 dBs. So the difference of sampling or a signal coming in here in this band and having it at the Nyquist frequency is already 3.92 dBs of attenuation on that because of the frequency response, the filtering nature of the sample and hold system. So we have to remember that. It's not as bad as this, as we are very unlikely to be operating at the maximum bandwidth because we've already decided that operating at the Nyquist frequency is not that easy anyway. This is just another problem that we have. So even if you only operate within a fraction of the bandwidth, if you operate at 80% of the Nyquist frequency, for example, you're still going to be down by 2.4 dBs. Remember, 3 dBs is a halving. So we can improve again our matters by increasing our sampling frequency without increasing our bandwidth. So we actually get some gains by oversampling even without the noise shaping stuff, and that will work quite nicely. Or we can apply some more complicated filtering to try and pre-compensate the frequency response in advance. So again, this is a reasonably well-known feature, but not that well-known that we don't have to teach it. So there are different ways of doing this. You can have a nice so the bandwidth of your input signal, in this case they're showing it's a sort of a flat response, but this whatever this is the thing that you need to faithfully reproduce at the output. So if we start with this as a basic principle, we can then put it through a digital filter in our before our D2A converter and pre-compensate the response. So we would actually emphasize the high frequencies. Feed it into our digital to analog converter, which unfortunately has a sine x over x response for this band here. And if we combine these two together, with any luck, we end up with the same bandwidth coming out the other end once we've done a low pass reconstruction filter on it. So that's fine. So all these are nice and linear, and we've done the pre-compensation in the digital world. The other way we can do it, obviously, is to take a signal of interest, D2A it, and accept there's going to be a falling off of the response to the higher frequencies. Do a low pass reconstruction to get it back to an analog system, and then do a emphasis filter on the output to give us this type of response, and this one combined together to give us again our faithful reproduction of our signal bandwidth. Right, so the question becomes then, how do we make one of these? Or, we could make one of these, but it's digital, we're not interested in that. So it turns out to be not that hard to do. We can actually just create something like this, which is a single response in there. And this prototype can be used to give 0.1 dB flatness up to 50% of Nyquist or so. So as long as we operate at 50% of the Nyquist frequency, then a simple output filter like this can give us a nice flat response up to that range. So this is the useful range of our band, where if we didn't do any of this, we'd end up with this response coming out of our DAC system. So be aware of the frequency response of sample and hold systems. Doesn't apply to sample and holds on the inputs of digital systems. It's just the way it's only if you're bringing signals out into the analog world, this frequency response actually applies. Okay, so I suspect that the easiest thing to do now will be for me to stop at that point, because that's an interesting point to stop at and be worrying. And what I will do is I will record another half hour or so on the remaining part of D2A. D2A is not that hard, and there isn't that much in there. We've done all the principles pretty much already anyway, but it just need to be shown how to do this. So I'll do that. I'll put half an hour worth in, and then if we've got time at the end of the course, I can go over any bits that people are interested in at that point. But otherwise we'll just get slightly into this and we'll have to stop anyway. So we'll stop at that point. Look out for the lecture that finishes this part of the module off, and then have a nice Easter. Yeah, I think that's all we need to say at the moment. You can probably start looking at the coursework over Easter. You will need, well, probably, I'll say that, probably you will need some of Kay Lee's material, of which some is already on the notes pages. But you don't need to know the detail of that to plan out your architecture and understand what's going on. So it'd be well worth your while planning your architecture for your radar system. You can do all the analog stuff certainly and get that up to speed. And if you go down the route of using a phase lock loop, which I highly recommend, the idea of voltage controlled oscillators and phase detectors, which you might need, will come later. But you can certainly look at the architecture now, I guess, and be time well spent over Easter. Okay, thanks for your time. See you next term.